All right then, yeah, so Tom pretty much nailed it on the head. So I'm going to describe to everyone what source sink studies are, why we conduct them on the Earth, why they're relevant to Mars, and a little bit about what we're doing in terms of preparations for Mars 2020. And hopefully by the end of this talk, you'll understand why I had the little addendum of "to see the world in a grain of sand." Why it's very much one of my favorite poetry parts and very much to do with source sink studies. So continuing on. There we go. So what are sediments? As I know, UKPF is a diverse group of scientists. I thought I'd start from the very beginning. So sediments are, in a nutshell, materials, bits of rock that's been broken down by processes of weathering and erosion. And then this material is subsequently transported according to the climate at the time. So it could be transported via wind, in rivers, in ice, in glaciers, or even just transported by gravity, and then deposited elsewhere. And so the background image on this slide is Mars, and you can very much see that sediments are everywhere on Mars. So understanding sediments, understanding their characteristics and why they came to be and why they've formed these rocks is kind of key to understanding the environments of deposition and also all the other processes that form them too. So on the right hand side, I have a little chart for of grain size, Wentworth grain size classification. You can classify sediments in a lot of different ways, but grain size is one of the kind of most important ones. And so whenever I say things like sand or gravel, I'm referring to a specific grain size fraction and not mineralogy or geochemistry. But yeah, as such, sedimentary rocks, we need to understand sedimentary rocks and why they exist on Mars, their environmental formation, and how this could have changed over the years. Apologies for the squawking in the background. There is a bird in my room. I'm looking after my neighbor's bird. So. Anyways, Mars's ancient environments. So Mars's sedimentary record is pretty diverse. We see from orbital studies, especially in the older crust, so crust older than 3 billion years old. We see lots of evidence that water existed on the surface of Mars and has influenced the geological record as a result. So this image in the top left-hand side is an example of an inverted fluvial channel. And here is a map from Davis et al. 2016 of Arabia Terra, showing the extent to which there are all these valley networks and inverted channels. So it shows that there's lots of geomorphological evidence that these features are abundant. So there was lots of fluvial action, especially in this area in the past. Another example of how we know there was surface water on Mars in the past is through mineral assemblages detected from orbit. So there's lots of hydrous mineral assemblages detected all over Mars, especially like phyllosilicates or clay minerals and sulfates. And so all of these hydrous mineral assemblages require liquid water to form. This is more evidence that in the past, Mars was warmer and wetter than the dry and cold climate that we see today. So as a result, warm and wet Mars is pretty exciting, especially from an astrobiological point of view. So this is why there's been all these landers and rovers sent to the surface of Mars, and rovers that will hopefully reach Mars in the future with Mars 2020 and ExoMars, to go and investigate some of these sites in more detail. So yeah, Mars missions are sent to investigate whether or not life may have existed or potentially still exists on Mars. So purely environmental studies are very important for the success of these missions. But as Mars missions have this kind of astrobiological primary mission aim, all of these places we send rovers and landers are largely sedimentary in nature. So we don't really have as much in situ analyses, with the exception of Spirit rover that went to Goethals Crater, of igneous rocks. So in order to kind of like understand the diversity of the Martian crust, source to sink studies also play a role there. And so here's a schematic of the idea of source to sink studies, and essentially you start off with the lithified rock that will have gone through all of these processes, and you kind of work backwards to find out what the initial source rock was, and try and delineate all the different sedimentary processes from each other to give a best estimate as what the initial source rocks were. So some examples of how source rocks influence sediments on the Earth. So you see on the left-hand side an image of Reynisfjara beach in Iceland, and it's very different in colour and appearance compared to Alona beach in the Philippines on the right-hand side, which is a white sand beach. And these differences directly relate to the source rocks, whereby Reynisfjara beach in Iceland was eroded from Reynisfjall mountain and the surrounding basaltic rocks. These are all volcanic rocks, which are very dark and glassy in nature, compared to Alona beach in the Philippines, which has been eroded from the Maribyrnong limestone formation, which you see here exposed in Chocolate Hills after a earthquake hit the area. Another example of how sediments can preserve the characteristics of the environment of deposition and transportation. On the left, you have an example of Yellowstone Lake in Montana, very nice, quiet, serene lake environment. On the right-hand side, you've got a Balkan dune from Samsi in Sahara. And you see these sediments themselves are very different in appearance. And when they become buried and lithified, the rocks themselves are very characteristic. So Curiosity's investigation of Gale Crater is kind of to try and investigate the sedimentary record in Gale Crater and try and understand a bit more about Mars's past and how the climate's evolved and stuff like that. So Curiosity went to Gale Crater in 2011, landed in 2012. And the reason Gale Crater was selected is because it's got this 5-kilometer high mound of stratified rock in the center. This mound is called, informally known as Mount Sharp. And from orbital studies, the strata in the lower part of Mount Sharp showed these signatures of these hydrous alteration mineral assemblages like phyllosilicates and sulfates. In the upper part of Mount Sharp, these hydrous mineral assemblages weren't detected from orbit. So it suggests that Mount Sharp in of itself, this geological record, it's preserved some kind of changing, possible climatic shift. And so Curiosity went there in 2012 with a suite of instruments to try and investigate this rock record. So Curiosity's other name is the Mars Science Laboratory, or MSR, because it's literally a laboratory on wheels. And it's got all of its instruments, gives it its capabilities to investigate the rock record. It can clean rock surfaces with a brush, so then it can analyze the rock surfaces with bulk geochemistry using APXS, XRF spectrometer on the rover arm. It can also have very high resolution close-up images from the Marley camera, which is the Mars hand lens imager. Has the ability to drill and scoop samples, sedimentary samples, into its rover body, where it's analysed by Chemin, which uses X-ray diffraction to determine the mineralogy of the samples, and this is passed to the SAM instrument, which looks at the volatiles in the samples and the isotopes present, and it can also do that for the atmosphere too. And Curiosity's also got ChemCam, which is another geochemical instrument that fired the laser up to 7 meters away from the rover mast to get geochemical compositions of geological targets. And you've got a series of science cameras as well, like MassCam, which also has visible near-infrared spectroscopy, and MARDI, which is the descent imager, but is also still used to take pictures of the bedrock underneath Curiosity River. So Curiosity has done a great job so far. It's been there for over 8 years now. It's analysed 28 successful drill samples, 3 successful scoop samples, driven over 14.4 miles, over 400 meters of elevation. So this is over 400 meters of stratigraphic rock record, and there's been over 800,000 ChemCam laser shots. So it's a lot of data coming from Curiosity in terms of that can help us interpret this rock record on Mars. The current interpretation for how these geological rocks form, the paleo environment, is we have these sandstones in the Bradbury group. Bradbury group was the sedimentary rocks analysed before we got to Mount Sharp. And in this area in particular, this is the Kimberley Formation, and you had these what we call cliniform dipping sandstones with all the mudstones in the Mount Sharp group at the end. And this very much indicated provided evidence for kind of deposition in where rivers flow into a standing water body and deposit out these deltas, which form these kind of cliniform features in the sandstone, and then you get your nicely stratified mudstones in Mount Sharp, in the Mount Sharp Formation. And so looking at the Kennen analyses throughout the traverse, there are some changes in mineralogy, particularly for the mudstones, that could reflect variations in the ancient environment. So you see here at Yellowknife Bay and up to Marius Pass area, you get some phyllosilicates plus magnetite, which is this little black wedge, and you also have feldspar and mafic igneous minerals present. Then you reach Marius Pass area, you get a bunch of crystalline silica and an increase in magnetite. And then after that, you kind of start to see more hematite present, which is this red wedge. Fewer mafic igneous minerals, which is the light grey wedge, and you see lots of phyllosilicates come back. And so this could potentially indicate that up to this point, you had this perennial lake environment. And then around where we started to see the hematite become more abundant, we also came across this outcrop. So this is the old Soka outcrop. And you see that it's got mud cracks, which indicates that in this area, at least, the lake waters kind of at least retreated away from this area. And so it could represent seasonal, some drying that has occurred to create these mud cracks. And as you go up, you see hematite abundances increase as well. So this is an artist's impression of Gale crater in the past. So you have these rivers flowing into the standing lake body. And this is another interpretation by Hurwitz et al. In 2017. Why you have these variations in mineralogy, and especially why you get this kind of increase in magnetite in your crystalline silica in the deeper lake waters compared to your hematite and phyllosilicates. They're present in the shallower lake waters and may have experienced occasional drying from seasonal variations. And so that's the environment. So thinking about the source rocks. So as I mentioned, in Gale crater, we don't really have any nice exposures of some volcanic flows or anything to be able to analyze in situ with curiosity, but there have been a series of pebbles and so these large clasts in conglomerates. This is the Harrison clast in a conglomerate in the Bradbury group. And there's also been a series of float with igneous textures in, such as porphyritic or aphanitic textures. So a study by Peter Edwards in 2017 has showed, if you look at the blue contours, where density contours are kind of two-dimensional histograms, and you have the bulk of your data set plotted within the foci, you see there are two groups. One is pretty basaltic, one is trachybasaltic, already indicating that there is actually a fair bit of geochemical diversity from the source rocks from which these pebbles and float were eroded from. Looking at the sediments themselves, so now in the sandstones and the mudstones, so there have been a couple of studies, one by Seebach in 2017, looking primarily at APXS data, and one by myself, sorry, that should say 2019. But the APXS team, they looked at the different grain size fractions and saw that there was some geochemical variation associated with the different grain size fractions. So overall, and this related to variations in mineralogy as well for different grain size fractions. So overall, your conglomerates and your sandstones have a higher proportion of feldspar, which you have felsic minerals, compared to your finer grain sediments that have a higher proportion of mafic minerals, such as olivine and pyroxene. And so with the exception of the Kimberley Formation that does have distinct mineralogy with the sanidine present, it seemed to indicate that potentially mineral sorting, so physical grain segregation, as these sediments were transported in a river environment and deposited in a lake environment, could have caused this geochemical variation. For the ChemCam data, where this little cross up here by the 10 to the 1, on the y-axis, this is the errors. Here again, we've got density contours from different groups. The light green is Bradbury, dark green is Mount Sharp, and the grey is your igneous floating class from Edwards et al. I teased out 5 different bulk compositions that I interpreted as relating to variations in source rock. You can see, especially with the Mount Sharp group, that being distinct from the Bradbury group, and the pink dots are from the Kimberley Formation with your sanidine, thought to be derived from a more trachybasaltic source, and the silica-rich Marius Pass mudstones with the tridymite, which may have been derived from a more rhyolitic source. However, sorting versus source is one of the big questions on Mars with interpreting this geochemistry and the mineralogy. Mars's sediments are largely basaltic, so they have different physical, geochemical, and mineralogical properties compared to most sediments on the Earth. As a result, the majority of conclusions for your Mars source to sink studies are based on modeling laboratory results. There are some terrestrial analog results, but there's not as many. So more work kind of needs to be done to ground truth these hypotheses, and especially to when it comes to debating about sorting versus source influence on Mars. Another issue with Mars rover studies compared to terrestrial studies. So on the Earth, when you go out and look at your sedimentary environments, you have direct access to your samples, you can pick them up, you can look at them with a hand lens, you can look at them in the fin section, you have a lot of, whatever laboratory analyses you want to do on them, you can pretty much go and do. You can also freely explore the field site. And in a lot of cases, you have direct access to or you can go and sample the source rocks as well. On Mars, there is, all your sample analysis is pretty much done through source to sink techniques used on the Earth. You've got limitations on field site exploration. You can only really go where the rover's traversing, and you've got limitations on like power constraints and time, and you don't always have your direct access to the source rocks. So there's also a question into, you have this difference in Earth-based source to sink studies and Mars-based source to sink studies. So how effective are Mars source to sink studies when you only have the rover's techniques to use and you don't necessarily have this knowledge of the source rocks? So this is another question, how effective are they at actually delineating these source to sink processes? And the other big question, so we've got Mars 2020, that's going to land in February next year. And it's going to Jezero Crater. Jezero Crater has got this lovely delta fan feature. It's going to land somewhere around this delta fan, which is indicative of, as I mentioned before, a river channel coming in and entering into the standing water body, deposit all these sediment, creating this fan-like feature, similar to how the Mississippi River Delta is formed. So Jezero is a place of interest, so going there in Mars 2020, artist's interpretation of it then. And it's going to have some new capabilities. So you're going to have new instrument techniques for the Mars 2020 mission. You've got a Mars helicopter, can collect samples to return to the Earth. In terms of new instrument techniques, we've got Raman spectroscopy that's going to be used. Instead of a bulk XRF instrument, there will be a micro XRF instrument. And we don't get bulk mineralogical analyses in the same way for Mars 2020 as we did for MSL. So there are some differences here. And there's also going to be autonomous software capabilities for Mars 2022. So another question is, how is this new technology going to influence how source to sink studies are conducted for Mars 2020 compared to MSL? And also, whenever you bring new technology in, like how is this going to affect science operations? So there's kind of this sorting versus source on Mars to-do list, whereby we need to kind of ground truth Mars's source to sink study techniques and the hypotheses of sortic environments across different environments. And also trial the new technology on the Mars 2020 mission and figure out the best kind of practices for science operations and data interpretation. So this is where our Mars analog mission comes in. So our Mars analog mission is called SANDI, also known as Semi-Autonomous Navigation for Detrital Environments. And the mission aims are to trial the effectiveness of novel techniques, such as UAS imagery, such as that would be returned from the Mars copter Ingenuity, and autonomous software in tactical decision-making. And also another mission aim is to investigate the changes in physical and chemical properties of basaltic sediments as they're transported in fluvial and aeolian environments. So Iceland's a good Mars analog, as on the Earth we have all three kinds of crust, primary, secondary, and tertiary. On Mars you only really have primary and secondary. Iceland is a place on the Earth where you have secondary crust. You don't really have the influence of the tertiary crust. So it's a good place to look at because in terms of mineralogy, it's similar to what you see on Mars. And so you've got lots of volcanoes on Iceland, nowhere near in scale as what you see on Mars, but volcanoes are present. You also have other processes in Iceland, such as glaciers and ice caps that you get on Mars. And Iceland has rivers that, as I mentioned before, existed on Mars in the past, and also has areas where you have alien sand sheets, such as what you see on Mars. And so Iceland's a very good place to go and kind of investigate and figure out some of the answers to the questions that we have. And so our field site is located in southwest Iceland at the base of the Þórisjökull glacier, just to the north of the Reykjanes Peninsula. And we had 3 field sites from which we were going to do our analog field trials. One was proximal to the glacial, medial, and distal. We chose three field sites so we could try and analyze the sediments and investigate them for any effects of sorting, weathering, or influences of the local source rocks. We also have several large volcanoes in our area. We have the Litla Björnsvatn and Stora Björnsvatn subglacial volcanoes. There's the volcanics under the Þórisjökull glacier, which are also subglacial, and the large subaerial Skjaldbreiður shield volcano too. And so during our study, in addition to doing the sedimentary analyses in the field trials, we also went and sampled all of these volcanics. And so here we are, this is the start of the field trial, first time we came out. You can see Litla and Stora Björnsvatn in the background and Þórisjökull way in the distance, Skjaldbreiður to the other side of us. And here's our PI, Ryan, Professor Ryan Ewing at Texas A&M, helping us set up the tent. Here's the tent setup. See Skjaldbreiður there, looking all moody, his peak hidden by the clouds. And so our concept of operations for the field trials, we did at each proximal, medial, and distal site. We actually have 6 scenarios. The 6th scenario there is the standard human geologist scenario. So we'll just talk about scenarios 1 to 5 here. For each scenario, we had 5 stops and 5 drives for each traverse. And at each stop, we took visible near-infrared, 2 to 5 visible near-infrared analyses. So the reason we did visible near-infrared is because it's similar to what we would get from MassCam on MSL or MassCam-Z on Mars 2020. Also get portable XRF analyses, 2 at a maximum per stop, to be representative of the XRF analyses from the APXS instrument on MSL. Get 2 microimager analyses to kind of replicate what we would get from the Mars hand-lens imager. And every time we take an XRF analysis, we would also sample the sediment at the surface and underneath. So you get 4 samples at each stop as well. And the way we staffed it all was we'd have ground scientists who stayed in this tent, so they were completely oblivious to what was going on outside, except for they would just see what was happening through their computer screens as though they were in ground control on the Earth. And you then had a number of field scientists who would emulate the instruments on the rover and collect the field data for the ground scientists, as well as sample the sediments. And you had a documentarian who kind of ran around and recorded the decisions being made for the ground scientists and how long it took to do each analysis, and recorded the time for each setting. So our first scenario was a standard kind of MSL type scenario where we just had the rover, scientists on the Earth before landing would select sites of interest based on satellite imagery, and then the rover would land and return the initial images of the landing site through MassCam panoramas, and also would return a visible near-infrared spectroscopic measurement up to 2 meters at 2 meters in front of the rover. Then the scientists on the Earth in the Mission Control Center would select the targets and the next waypoint based on the downlink data. So here's an example of them selecting their targets and their rationale kind of behind it. Then once they'd select that, the field scientists and engineers would go out, acquire the measurements, collect the geological samples, move the rover to the next waypoint. And so then scenarios 2 and 3 is when the autonomous software would start to be involved. So this scenario 2, the rover would still kind of do its traverse, but the ground scientists would have the addition of the autonomous software data. And scenario 3 is what we call a rover walkabout. So the rover would do the entire traverse, and then all of the data, take lots of images and lots of autonomous software classification of said images, deliver that to the scientists, and then the scientists would look at the data from all the traverse and decide from that where they want the rover to stop. And then the rover would go back, stop at these sites, and you would get the geochemical analyses from that. And so this is a bit what the what ASAS looks like. So this is a hazard classification part of ASAS, where green represents surfaces that are okay to go, red is surfaces that are not okay for the rover to climb, and the yellow is kind of like risky, but you can have a think, look at the images and decide for yourself. So the hazard classification became quite useful actually for the ground scientists when we were at the proximal site where you have a lot of fluvial channels, and so there's a lot of kind of steep banks and that sometimes you can't see from mass cam images, and so the ground scientists weren't aware of them until the rover tried to do the traverse, and then it saw that there was a steep drop. So the autonomous software for the hazard was useful there. For the classification side of it, and geological classification, the geologists didn't use it as much during these field trials, but we're now working with engineers to optimize the geological classification for our field trial next year. And then scenario 4 and scenario 5, this incorporates the UAS image, so images from drones to represent the Mars copter Ingenuity. Scenario 4, we just took drone imagery around 40 meters by 60 meters around the rover. And then scenario 5, the drone would do a full reconnaissance of the area and give us kind of a higher resolution map than what we would just have from the standard satellite imagery, by which we would then use that to determine the waypoints for the traverse. And so here is a little video from the drone watching the field scientists working and taking the sampling. And we found when we were using the drone studies, the drone images, it was definitely a lot more useful in terms of identifying certain features, particularly aeolian ripples. They're easier to identify from the aerial footage at the higher resolution, and also for identifying some hazards and waypoints of interest. Having that higher scale resolution also aided in the confidence of the scientists in terms of deciding where to go next. So we've got this lovely data set, done all of the analyzed the 3 field sites and the source rocks. So now it comes to the point where we're going to kind of discuss how this could relate to understanding, testing the hypotheses of the source to sink studies we did on Mars through MSL, and also just like looking at the effectiveness of rover techniques versus when you can get that little bit more information from when you can look at the sample directly and use other methods such as optical microscopy, etc. So for source to sink studies on Mars, you kind of have this workflow. This is a different method, as I mentioned before, compared to what you do on the Earth. So kind of start off with a working hypothesis. Your environment, is this sedimentary, is this igneous? And you kind of determine that through both the orbital images and also some images from the rover. And then you kind of refine, you start classifying the different geological targets according to texture, so grain size, color, grain shape, using the aerial and river-based images again. And then you would further refine that classification with the chemistry and mineralogy from the various geochemical and mineralogical instruments to be able to build up this geological, this kind of understanding of geology of the area and how this could relate to the source rocks or other sedimentary processes such as weathering and transport. So I mentioned our analog instruments in the field. So during this talk, I'm not going to be discussing much about the visible near infrared aspect of our study. But for that, if you want to know more information on that, I'd refer you to Sinha L 2020, the LPSC abstract from him. And we're not also, but then once we collected the sedimentary samples, we would then analyze them in the lab. So we've got portable XRF, sorry, not portable XRF, micro XRF being analyzed at Texas A&M University. Again, we're not going to be talking about the micro-XRF results to in this talk, but if you want to learn more, then I'll refer you to Champion et al. 2020 LPSC abstract. But we also have been doing some XRD analyses at NASA JSC to be analogous to what we get from Canon, although with the lockdown, we haven't managed to do too many XRD analyses, but I'll show you the preliminary results anyways from there. So thinking about the results in relation to starting off our classification, coming up with our working hypothesis. So it looks as though there's lots of sedimentary features indicative of fluvial activity and aeolian reworking of the sediments at each field site. So you can see in the proximal field site, there are these fluvial channels with some finer grained kind of muddy, silty drapes. You've also got lots of large pebbles, cobbles, and lots of dark sand that's occasionally rippled. Whereas in the medial site, you still have some fluvial channels, but there's also this kind of prevalence of, you have a lot of aeolian ripples. There's a lot more activity, aeolian activity at the medial site. Here is, this is a UAS image, and you can see there's also more lava outcrops present in the medial site and boulders brecciated around the lava outcrop. Then the distal site, you have again your light tone silt deposits and some fluvial channels that appear to be older, and you also have some large aeolian bed forms at the distal site. So going through and classifying this according to grain size. So we classify this according to 3 main grain size groups. They have the silts on mud, which are less than 0.06 millimeters. The sand, and although there are lots of different ways you can subclassify sand, we stick to just calling this sand grain size. As you can see, that the sand grain size can be kind of mixed. So overall, this is average. On average, this is within the sand grain size fraction. And you also have the gravel grain size fraction as well, which is anything over 2 millimeters. And so once we have that, it moves along, there we go. So we've got our nominal classifications, our working hypotheses of these different sedimentary environments. Now you can go and look at the chemistry and mineralogy of our samples. So looking specifically at the gravel grain size, you can see in the box plots, you have the greatest diversity of gravel grain size, gravel geochemistry at the proximal site, sorry. And then this diversity appears to decrease as you go down to the distal site. Looking at the images, you can very much see the gravels in the proximal site are pretty coarse grained, pretty well rounded. To get to the medial site, they're a lot finer grained, and then the distal site, the pretty much looks like boulders brecciated. That's very similar in appearance to the local bedrock. So then looking at the geochemistry, and what we do with the images, we do what we call a decorrelation stretch. And the decorrelation stretch enhances the color separation of geological targets in an image. So the proximal site, the spectroscopists on the team aligned all these cobbles so that you can see in one image the diversity of the gravel grain size fraction at the proximal site compared to the distal site, where everything kind of looks very similar to the bedrock, and it's kind of all got this kind of greeny blue decorrelation stretches with some hints of red on various surfaces. So looking specifically at the grain site, the decorrelation stretch colors and how it relates to geochemistry. So the green decorrelation stretches appear to have higher magnesium and lower titanium. The blue ones appear to have kind of intermediate magnesium and titanium. Any red DCS cobble has kind of very low magnesium and a greater range in titanium compositions, which is kind of what you would expect from increase in weathering of basaltic materials. And you have this kind of odd one out and this unusual yellow cobble that we found at the proximal site. So you see the diversity largely decreases downstream. The dark squares show the cobbles from the proximal site, and they both kind of are in the red and the blue and green and yellow groups. But for the distal site, which are the light blue squares, they're largely blue and red. And these stars represent the compositions, the XRF analyses of your local outcrop. And so you also see that the blue kind of pebbles and cobbles and the blue pebbles and cobbles, sorry, from the medial and distal site are largely within this blue group, in which the outcrop compositions also kind of lie. So it appears as though as you go from proximal, medial, and distal, the gravel compositions and the gravel, the diversity of the gravel grain size fraction appears to be representative of your local bedrock. Another way we can test this is now we can compare this to our source rocks. So this is where we kind of go above and beyond. With our rover-based interpretation, we're saying pebbles and cobbles appear to be representative of local bedrock, and then we can compare this to these source rocks to actually see if this is correct. And so comparing this to the source rocks, you see the pretty crystalline green cobbles are very similar in appearance to this subaerial flow sample, which is from the capping unit of Libyan Spettel. Whereas the blue pebbles and cobbles are more similar in appearance to the subaerial flows from the scaled Breither shield volcano. The unusual yellow cobble is very similar in appearance to the subglacial, the tough tufaceous material in the subglacial volcanoes, especially relating to the stuff at the top of Libyan Spettel. And if you look at the trace elements, which are not as influenced by processes such as weathering and are relatively representative of different degrees of partial melting and fractional crystallization, you can see that where the contours are from the source rocks, the proximal pebbles have seem to span both the Little Libyan Spettel and Ceres-Yokutal volcanics and the scaled Breither volcanics, whereas as you move downstream to the medial and distal site, you have more pebbles derived from the scaled Breither and Strorobian Spettel volcanics. So it appears as though we were correct in our rover-based interpretation that the local bedrock does have quite a strong influence, particularly for the gravel compositions. So now going to the sand grain size fraction. The sands also show bulk geochemical and mineralogical variation with locality. You have the box plots again on the right-hand side, with the proximal site on the most right-hand side, and the dark diamonds are representative of average compositions. So you can see as you move downstream, you kind of have a slight increase in aluminium for the sands, a slight increase in magnesium, particularly in the distal sites compared to the proximal and medial, and a decrease in calcium. And so if you look at our preliminary XRD results, which are by no means finalized, we're still, once we get back in the labs, we'll analyze more, but from what we see so far, you do see that this kind of increased bump in magnesium could be representative of this bump in pyroxene you get in the distal sands compared to the medial and proximal. You get this decrease in amorphous component and kind of a slight increase in plagioclase at the medial, but then it kind of drops again in the distal sands. Then for the siltsoil muds, it also shows geochemical variation that's kind of similar to what we see for the sand grain size fraction, with the exception of magnesium. And so aluminium, you have kind of a more distinct increase in aluminium as you move from proximal to distal. For magnesium, yeah, it doesn't really change too much, but calcium again decreases. And then when you look at the mineralogy, so whereas before we had this bump in pyroxene at the distal site compared to proximal and medial, you don't really see this bump in pyroxene here. Whereas plagioclase, there's a definite increase as you go to the medial and distal. At least there's more plagioclase in the medial and distal sites compared to the proximal sites. So these variations appear to relate to variations in mineralogy, the geochemical variations. And so that in turn could relate to physical grain segregation, effects of weathering, increased weathering with transportation from the source, or changes in the source rock. So our study area is actually to the west of a study area from Mangold et al., where they looked at grain segregation in alien sediments for Icelandic sands. And so they showed in their sands, whenever you get an enrichment in olivine, you have an increase in iron, manganese, and magnesium, and a decrease in silica. And this kind of trend has been seen in Martian sands as well. For our study area, if you assume the blue and green gravel is kind of the composition, similar compositions for the local bedrock. So this is assuming we have no knowledge of the source rocks. So we take the blue and green gravel field as our local compositions, source rock compositions. You see actually there isn't that much variation in the sands compared to the local source rocks for our field sites. So it looks as though especially the sand grain size fractions are poorly sorted. However, if you look at the mud grain size fraction, which are represented by these stars, there is overall a much lower concentration of magnesium, iron, and manganese, and a slightly greater concentration of silica compared to what you see for the sand grain size fraction. So if you compare this to the mineralogy from XRD, you do see that in the sand grain size, the silt and mud grain size fractions shown by these kind of stripy bars compared to the sand grain size fraction, which are the non-stripy bars. Overall, silts and muds do have a much higher abundance of feldspar, especially at the medial site, and overall a slightly lower abundance of your olivines and pyroxene compared to the sands. So this seems to suggest that although sorting has had relatively little effect on the sands, the plagioclase feldspar seems to partition more strongly into the mud or silt grain size fractions compared to the sand grain size fractions. Looking at the sands specifically and dividing them according to the different environments, so the fluvial deposits and the aeolian deposits, we also see that overall aeolian sands had a larger geochemical variation compared to aeolian sands. So the fluvial sands, if you look at the GIF, they kind of have a lot more scatter around the compositions on the X and Y axis, whereas the aeolian sands are kind of a lot more uniform. You have a few that trends towards the higher magnesium, iron, and manganese compositions, but overall they are kind of much more closely clustered together. And so it appears to suggest that aeolian sediments are better sorted than the fluvial sediments. So looking at the images, the close-up images, this kind of supports what we've been seeing geochemically, whereby the fluvial sands have this kind of range in grain size. You have quite a diversity in class. You've got some yellow grains, some kind of porphyritic grains. You have some grains, especially in the distal site, that appear to be representative of different individual mineral grains. Whereas for the aeolian sediments, they're just kind of the largely vesicular, glassy sand grains in the medial and distal sites. So this seems to support what we see geochemically. And although there does appear to be some fining of the average grain size fraction for the sands as you move from proximal to distal in the fluvial sands, it still seems pretty poorly sorted in terms of there being a big diversity of grains present there. So it doesn't appear as though the sorting of sands has influenced the sand grain size fraction. So it could provide some more evidence that perhaps any geochemical variations we see are more likely to relate to changes in source rock compared to changes associated with physical grain segregation or weathering. And so looking again at the trace elements as a guide for source rock variation, in the sediments, you see that the proximal site for the sands and the muds, you have more present within the Littlebiensviertel and Thurusjökull geochemical fields, whereas for the distal and the medial sands and muds, they definitely trend more towards the Sturubjörnsviertel and Skjaldbreide fields. And so Skjaldbreide is a volcanic flow here, Sturubjörnsviertel is this one here, Littlebiensviertel is here, and Thurusjökull is here. So it appears as though the further you go downstream with the sands, the more likely you are to have influences from the Skjaldbreide and Sturubjörnsviertel volcanic rocks compared to the Littlebiensviertel and Thurusjökull rocks. So it appears as though it does potentially relate more to variations in source. So to conclude, definitely seems as though rover-based techniques are effective in investigating source sink processes and basaltic sediments. From all of our conclusions derived from just looking at the rover data, and that it just further supported by what we see when we can do closer investigations using other techniques in the lab, for instance. For the finer grain size fraction, our field site, the influence of sorting versus changes in sediment source can be distinguished from the others. And feldspar, interestingly, is more dominant in the fluvial silts or muds compared to the sands. So looking at thin sections of the source rocks, you definitely see that feldspar is a microphenocryst phase, and so this could potentially be why it's more likely to partition into these siltsoil muds grain size fractions compared to the coarser olivine and phenocrysts in the igneous rocks. Alien sands are well sorted, glassy and little weathered, and fluvial sands appear poorly sorted and represent a mixture of the source rocks in the area. So that's everything, and I'm happy to take questions.